This is chapter 45, SANS from ionic micelles, in other words charged micelles. Ionic micelles use surfactants with charged head groups. Micelles form in order to screen the hydrophobic groups on the tail, surfactant tail. Let's introduce an ionic rod-like micelle system. It uses cationic surfactant cetyl trimethyl ammonium, vinyl benzoate, CTVB, in water, in this case deuterated water for contrast. It forms rod-like micelles. Actually, free radical polymerization is performed on the VB groups in order to obtain polymerized micelles. The VB groups are on the outer surface and the CTA groups are on the inner surface. Blue and red here. This is VB, this is CTA. So this is a schematics of the cylindrical or rod-like micelle. Well, let's look at SANS data. At low volume fraction, we get mainly the contribution from the form factor. When we increase the concentration, we see a peak show up. It's contribution from the inter-rod structure factor. Be analyzing the data for dilute, for low concentrations mostly. The scattering model, this is the scattering cross-section, proportional to the contrast factor, the rod fraction, volume fraction, the rod or particle volume, that's the single rod form factor, and this is the inter-rod structure factor. We added a Q-independent constant for background, incoherent background. The form factor for a rod, I've seen it before, involves orientational average, angular average here, and then the form factor amplitude F has two terms. One due to the rod length is just like the one for a slab of length L. The second one due to the rod radius is just like the one for a cylinder of radius R. For the structure factor, one has to use the Orstein-Zernike equation solved with the so-called mean spherical approximation. In other words, this closure relation is used for Coulomb interacting systems. The structure factor is small. We want still to see its effect. It's small. In other words, the structure factor is almost 1 for dilute solutions like here, but we still want to include it, even though it's a small effect. There is the structure factor. It's given in terms of this direct correlation function in Q space, and this is the expression here. These constant A, B, C, and F are given in the original publication by Hayter and Penfold. Note that only the isotropic phase can be modeled by the mean spherical approximation approach, because it was introduced for spherical particles. We're pushing it here and using it for rod-like particles, which is not completely correct, but we're arguing that in the isotropic phase, low concentration, the randomization of the rods doesn't create too much trouble. Note that if we were to increase the rod volume fraction, micelle volume fraction, we would get into a pneumatic phase where there is orientational disorder but starting to be a translational order, or the smectic phase where there is highly ordered structure, just like liquid crystals, orientationally as well as translationally. These are the main liquid crystal phases for rod-like particles, and our case is really here. In other words, we're not doing the orientational average of each rod, but we're doing the orientational average of the form factor times the structure factor. Fits to the SANS data. using the model for rods, and then the MSA. This is the contrast of the CTVB in deuterated water. This is the dielectric constant, which is used in the MSA model. That's the temperature around ambient. That's the volume fraction. In this case we fixed it, but then the radius and the rod length were varied, were allowed to float, and we get something like 21 angstroms for the radius and 184 angstroms for the length at ambient temperature. We also get a pretty small charge on the ion. This is the science data in blue, and the fit using the dilute model here. This is the structure factor here. It's almost 1, except at low Q. There is a small deviation here, I would say maybe 10% or less. One can also estimate the radius of gyration of the rod-like cylinders, radius R and length L. The radius gyration is given by this, in other words, square root of R squared over 2 plus L squared over 12. We had seen this once before. So the apparent radius of gyration at fixed volume fraction can be extrapolated to 0 volume fraction here. This is called the virial expansion, to obtain the radius of gyration, the true radius of gyration. And the infinite dilution limit is about 124 angstroms. So these are the apparent radius of gyration. When one increases the fraction, the rod fraction, and extrapolation gives us 124, but that's the infinite dilution limit. We can get also the length, rod length versus temperature from the fits. It behaves kind of linear behavior here. In other words, rods get longer when we heat up from 25 to 80 degrees C. And here change temperatures as well. Here we're showing the tabulated dielectric constant versus temperature. This is tabulated in the CRC Handbook of Chemistry and Physics. Final words. We have used the form factor for rod-like particles and the MSA structure factor, MSA closure with the Orton-Zennike equation or structure factor to do fitting to sense data, obtain some results. Let's cover a couple questions and answers. Name 2 possible closure relations used to solve the Orton-Zennike equation for particulate systems. Well, we have seen the Perkusiewicz with hard sphere interactions, and we also have seen the mean spherical approximation for Coulomb interactions. Question 4, what is the CMC? That's the critical micelle concentration. This is the surfactant concentration for which micelles form. Question 5, what's the radius gyration for cylindrical rod of radius R and length L? We have seen this is equal to square root R squared over 2 plus L squared over 12.